operates by storing and releasing electrical energy in an electric field between two conductive plates separated by an insulating material, dielectric. Here's a breakdown of how it works. Structure. Electrodes, placed close to each other but separated by a dielectric, an insulating material like air, plastic, or ceramic. The dielectric prevents the plates from touching each other directly, allowing the capacitor to hold a charge, without allowing current to flow freely between the plates. Electrons accumulate on the negative plate and are removed from the positive plate, creating a potential difference, voltage, across the plates. This buildup of charge creates an electric field in the dielectric, which stores energy. 3. Storing energy. The energy is stored in the electric field created between the plates. The amount of energy stored depends on the capacitance, a property defined by the size of the plates, distance between them, and the dielectric material, and the applied voltage. 4. Discharging. When the capacitor is connected to a circuit, it releases its stored energy by allowing current to flow, effectively discharging as the charge moves back to balance the system. In summary, a capacitor temporarily stores electrical energy in an electric field and releases it when needed, making it useful in filtering, smoothing, and timing applications in electronic circuits. The key factors affecting its operation are the capacitance, the applied voltage, and the dielectric properties. Of a capacitor, which is its ability to store charge, depends on both the area of the plates and the separation between them. Here's how these factors affect it. 1. Plate area, A. Increasing the area of the plates allows more electric field lines to form between them, which increases the capacitor's ability to store charge. Larger plate areas result in higher capacitance because more charge can be stored for a given voltage. The capacitance C is directly proportional to the plate area. This affects the strength of the electric field. A smaller distance means a stronger electric field and thus a higher capacitance. Capacitance is inversely proportional to the separation distance between the plates. See Prop 2 Frac 1D. Therefore, reducing the separation increases capacitance, but only to a practical limit where the dielectric material can withstand the electric field without breaking down. The formula for capacitance C of a parallel plate capacitor is given by C equals frac var epsilon A D, where C is the capacitance in farads, var epsilon is the permittivity of the dielectric material between the plates, A is the area of each plate in square meters, and D is the separation between the plates in meters. This relationship is electric, ceramic material, e.g. titanium dioxide or barium titanate. Characteristics: small, inexpensive, and available in a range of capacitance values. Generally have low inductance and good frequency stability. Use: decoupling, filtering, and timing circuits in general electronics, especially at high frequencies. 2 electrolytic capacitors. Dielectric, a thin oxide layer formed chemically on the aluminum or tantalum plate. Characteristics: high capacitance in a small package, but generally polarized, can only be used with DC voltages in a certain direction. Use: power supply filtering, energy storage, and coupling applications in low-frequency circuits. 3. Film capacitors. Dielectric, thin plastic films, e.g. polyester, polypropylene, or polystyrene. Characteristics: stable, reliable, and with relatively low leakage currents, often non-polarized and good for high-frequency applications. Use signal coupling, timing circuits, and AC applications like motor run capacitors. 4. Mica capacitors. Dielectric, mica, a mineral with stable and high dielectric strength. Characteristics: high accuracy, low leakage, and excellent stability over temperature and frequency ranges. Use RF circuits, oscillators, and precision circuits requiring stability. 5. Supercapacitors or ultracapacitors. Dielectric, double layer capacitance at an electrode-electrolyte interface. Characteristics: very high capacitance values capable of storing large amounts of energy but with relatively low voltage ratings. Use: energy storage, backup power, and power supply smoothing in energy-demanding applications like electric vehicles. 2. Uses of capacitance including energy storage, storing energy for short bursts of power, as in supercapacitors for backup power and energy recovery. Filtering, smoothing out voltage fluctuations in power supplies and removing unwanted noise in audio and signal processing circuits. Coupling and decoupling, blocking DC while allowing AC signals to pass, used in audio and radio circuits for signal transmission. Timing and oscillators, used in RC, resistor capacitor, and LC, inductor capacitor circuits to create time delays, set frequencies, and control oscillators. Tuning, used in tuning circuits, e.g. in radios, to select specific frequencies. In summary, the dielectric material influences the capacitor's stability, voltage rating, and application suitability, making it crucial in selecting the right type of capacitor for different electronic needs.